Although it's unlikely we would do a calculation with the equation Ke equals 1/2 mv squared, it is important to think about everything that that equation can tell us in relation to particles, and in this case, specifically gas particles. So this is a given equation because we want to understand and remember that kinetic energy, a measure of the temperature of a sample, is related to both the mass and the velocity of that. So when I compare one gas to another, I may see some differences, even if at the same temperature. And if I compare the same gas at different temperatures, I would see some differences as well. The way we normally represent this, besides just talking fast and slow and more and less, is a graph called a Maxwell-Boltzmann distribution. That's named after two people who did lots of studies with thermodynamics. This connects to kinetics, this connects to thermochemistry and thermodynamics, but it's also very important for understanding the behavior of gases. Even though we talk about hot as fast and maybe cold as slow in terms of particle motion, in a specific sample, we've got more than billions of molecules, and they're actually moving at quite different speeds. There's a big difference in maybe the highest and fastest moving particle and the coldest or slowest moving particle. We can represent that or think about that by graphing the speed of molecules versus the number of molecules that are moving at that speed. When we talk about average kinetic energy related to temperature, when we're looking at this, there's lots of different ways that we could kind of define average mathematically. Because I've got a velocity and I've got a square root, there's root mean squares, there's square roots, there's just averages. Really, we're kind of just thinking kind of all of those averages together, almost as if we're looking at the mean, median, and mode all at once. But we would say if I had a cold gas, most of my particles would have a very low speed. So as I look at the x-axis and as I look at my sample defined as a cold gas, I have a whole bunch of particles with this speed. I have some particles with a little bit slower, some particles that are a little bit faster, fewer particles that are really slow, fewer particles that are really fast, but I have a distribution here. It is cold, so there's not very much spread there, or really a lot of it is kind of defined by a small range of potential speeds for my particles. When I heat it up, my particles speed up. That doesn't mean that every single particle gets the exact same amount faster. My average kinetic energy, however, does increase. So what we have here is kind of a standard distribution curve, but it's cut off a little bit by the fact that there is a minimum temperature of absolute zero in some of these cases. But I've got a nice distribution here. A few of my particles are moving really fast, and we notice that many of my particles are faster or have a higher speed than they had previously. But my graph isn't quite as tall because there's more possible speeds that they can be moving at. Fewer of them are moving at any specific speed. So if we had a test with 20 questions, there might be a whole bunch who got 10 right. But if we had a test with 30 or 40 questions, we would spread out a little bit more. It doesn't mean that fewer people took the test, but it does mean that there's kind of a shift in our distribution curve, and maybe fewer people got that average number there. But most of my particles are at a higher speed than they were there. If I make it even hotter, it spreads out further. I still have a few cold particles, but compared to the room temperature in the cold gas, far, far, far fewer. Many more of them are further to the right or are at a higher speed. So for all of these, the area under the curve is the same. We are shifting it further to the right to show that a higher percentage of my particles are moving at a faster speed. If I have different gases at the same temperature, I would have the same average kinetic energy. That does not mean the same average speed. With the equation here, Ke is 1/2 mv squared, for them to have the same kinetic energy but different masses, we would see an inverse relationship between speed and mass. It's not a directly inverse because we do have a square in there, but for our purposes, we just see one go up and the other go down. For example, we have several noble gases here. Helium at a certain temperature, in order to have the same kinetic energy as xenon at that same temperature, the helium is significantly lighter. It is 30 times lighter or more than my xenon here. So my helium is very flat and wide, showing me that many of my particles have a higher speed than my xenon. The higher velocity accounts for the lower mass, and mass times velocity would give me the same kinetic energy for helium that maybe a big mass and low velocity on average would give me for xenon. If we are comparing gases at the same temperature, but they are different gases, or even the same gas at different temperatures, we do want to define what's the same. So to compare helium to neon to argon to xenon at the same temperature, they have the same kinetic energy, which is why as mass goes up, our particles would slow down. If we had the same gas at different temperatures, we would recognize, well, the kinetic energy is changing, but it's the same gas. So we have the same mass. That means higher velocity or lower velocity based upon the temperature. One way we can measure or observe the speed of these is how they move around. Two measurable or two macroscopic properties would be diffusion, the way gases or anything spreads out. Like if you spray perfume in one corner, how long until it's smelled somewhere else? Or you could do it with liquids, dropping a single drop of food coloring into water and watching it mix throughout. Or effusion. This is more specific to gases and how fast they would move or escape through a small hole. Effusion is a little bit simpler to model for our purposes in terms of an equation, and it's not even one that we would directly do a calculation with, but there is this simple equation here that Graham's law of effusion tells us that our rate of effusion, which has to do with how fast the particles are moving, is related to molar mass. Well, my rate for my first gas compared to my second gas, we see an inverse relationship here. Higher the rate is due to a lower mass. So heavier things move more slowly, but even more so because we have a square in terms of our velocity here. It is related to the square root of our mass. So we would not need to do exact perfect calculations, but we could understand that the lighter the gas, the faster it moves, and that is related to the square root of the mass, or in this case, the molar mass of our gas.